How does system modeling reveal hidden system behavior? Imagine trying to understand a complex machine just by watching it run. You might see how it moves or sounds, but some behaviors stay out of sight. That's where system modeling comes in. It's like creating a detailed map of how all parts of a system work together, even the ones you can't see directly. By building models using math or computer simulations, engineers can see how a system reacts under different conditions. These models help uncover behaviors that are not obvious at first glance. For example, some systems might respond in unexpected ways when pushed to certain limits or when multiple parts interact at once. Starting with the basics, system modeling involves defining the key parts of the system, called state variables. These variables describe the current condition of the system and its history. Inputs are the signals or forces that influence the system, while outputs are what we observe or measure. Using equations called differential or difference equations, the model captures how the system changes over time. This allows engineers to predict future behavior based on what is happening now and what happened before. Another important idea is encapsulation. It means hiding the internal details of subsystems behind clear interfaces. This makes it easier to analyze how different parts connect and work together without getting lost in every tiny detail. By focusing on how energy, information, or materials flow between parts, engineers can spot behaviors that might otherwise stay hidden. Running simulations with different input scenarios reveals a lot. For instance, oscillations or unstable responses might only show up when certain conditions are met. Nonlinear responses, where the system behaves differently at different input levels, become clear. Time delays and transient behaviors, which affect how quickly a system reacts, are also easier to see. Take a mechanical example like a direct current motor. Modeling it involves representing its electrical and mechanical parts and how they convert energy. When engineers simulate this model, they might discover hidden dynamics like torque ripple or overshoot during startup. These are behaviors that aren't obvious just by looking at the motor but become clear through modeling. System modeling also uses state space analysis, where the entire system is described as a collection of variables. This helps engineers study stability, controllability, and how well they can influence the system with controllers. It shows which internal states impact outputs and how feedback can be used to keep the system stable or improve performance. In real-world applications, system modeling is essential. It helps predict failures, optimize how systems work, and design controllers that can handle hidden dynamics. Advanced techniques like machine learning can be combined with models to find patterns and behaviors that traditional methods might miss. Overall, system modeling acts as a powerful tool to reveal behaviors that are not immediately visible. It provides a clear picture of how complex interactions unfold over time, helping engineers understand, predict, and improve system performance in ways that simple observation cannot achieve.